So for today, okay, first thing we started talking about in this unit, okay, was simple harmonic motion, right? And obviously you need to know, okay, what it is and why it happens. Okay, and by the what and why, okay, it's any motion that repeats a cyclic pattern. Okay? Those cyclic patterns happen because restoring force varies linearly with displacement. Okay? That's a key. That's Hooke's law, basically. Okay? He's the one who discovered that. But that has to occur in order for simple harmonic motion to start and be maintained. Okay? Restoring force has to vary linearly with displacement. And then we looked at the two examples of simple harmonic motion that we're going to talk about in this course. And that was, okay, the mass on the spring. What affects the period of a mass on a spring?
Mass and spring.
The mass and the spring constant, right? Okay, so we could calculate the period of a mass on a spring with that formula. Is that something you might be expected to do on your test? Okay, in the written response, for sure. Okay. And the other simple harmonic oscillator we talked about was a pendulum, and we did a lab on that. What affects the period of a pendulum? Length and gravity, right? Okay, so I would expect that since we did a lab on that one, there might be a little bit more in the multiple choice about that one in terms of understanding what affects its period, okay? But also expect a problem-solving problem to do with the period of a pendulum in the written response. All right, so that was the first few days of the unit, all right? Then we talked about Hooke's law. Okay, so Hooke's law says that this restoring force varies linearly with displacement. Force in a spring is equal to negative kx. Okay, so it's important that we understand that. There could be a multiple choice question, okay, about Hooke's law, but it's also important that we're able to use that to solve problems, because there'll be a Hooke's law problem in your written response as well. Now, what we talked about most often with Hooke's law was the stretching of a spring due to a mass hanging from it, just like Hooke did when he initially came up with this idea. Okay? He had springs hanging from the ceiling, and he would put masses on them and record how much they stretched. What force is stretching that spring? If I hang something from it. Gravity. Okay? Well, since the thing's not oscillating, okay, it's not going up and down, okay, it's not moving at all, in fact, what's the net force? Zero. Okay? So that means that, okay, the force in the spring plus the force of gravity would equal 0 in that situation, which basically means the force in the spring is equal to the force of gravity, in opposite, but opposite in direction, obviously. Okay. And that was kind of our most common situation for Hooke's law. Hint, hint, it might be the one on your test. Okay, so make sure you can solve a Hooke's law problem. Now, the problem with Hooke's law problems is they appear to give you similar data to a law of conservation of energy question. They would give you spring constant, displacement, things like that. What will a law of conservation of energy question give you that a Hooke's law question will never give you? Speed. Okay? Hooke's law is about the stretching of a spring, not about how fast something is moving. Okay? You could get a law of conservation of energy question and then have a part B that would be a Hooke's law question. but that part of the question would only ask you about one point and how much it was being stretched, or what force was involved, or what the acceleration was. None of that stuff ever ends up in a law of conservation of energy question. Okay? A law of conservation of energy question never talks about force, never talks about acceleration. Okay? So that's how we tell them apart. Okay? They give us similar data, displacements, spring constants, things like that. Okay? But there are some things that we would only find in conservation of energy, velocity or speed. Okay? And some things that we would only find in a Hooke's law question, force and acceleration. Okay? Those would not be part of a conservation of energy question. All right? So just be aware of that. Okay? Questions on Hooke's law? Then conservation of energy. Now we talked about this because, not because we needed to review what conservation of energy was. We already know how law of conservation of energy works. Okay? And that is that EI equals EF. Okay? Our initial mechanical energy equals our final mechanical energy. We talked about it in two contexts. A pendulum. Okay? As a pendulum swings through its arc, it's converting its potential energy into kinetic energy back into potential energy, right? But a pendulum works just like a roller coaster because it uses what kind of potential energy? Well, actually, they're all mechanical. Due to gravity, yeah, gravitational potential energy. Okay? Whereas a mass on a spring okay, it doesn't use gravitational potential energy, it uses elastic potential energy. Okay? So over here, our potential would be m times g times h, but over here, our potential would be 1/2 kx squared. Okay? Elastic potential energy. And remember where we got that formula from. Okay? We got that formula from something we learned in Science 10. Okay? On a force distance graph, okay, according to Hooke's law, the more force I apply, the more the spring will stretch. Well, the area underneath this line is the elastic potential energy. Okay? And it's 1/2 the base, which is distance, okay, times the height, okay, which is force. Well, remember that when we're talking about Hooke's law, the force is kx and the distance is x, 1/2 kx squared. Okay, that's where we got that from. Right? It's really just force times distance, okay, getting us the average, okay, there. That's why the half's there. All right, so how do we recognize the conservation of energy question? It'll talk about two different points. Okay, a Hooke's law question will only talk about one point, okay, and it'll have some mention of speed, okay, that a Hooke's law question would not have. Right? It's always going to be comparing two points. All right. If this is our equilibrium position right here, okay, what kind of energy does the box have at equilibrium?
Just potential.
The opposite.
All kinetic.
All kinetic energy. Okay, remember guys, if we're looking at our potential energy formula here, x is the displacement from equilibrium. If we're at equilibrium, what's x? 0. Okay, there's no potential energy at equilibrium because x is 0, and because when x is 0, the spring is neither stretched nor compressed, which means it can't push, which means there's no potential. Okay? There's nothing there to store any energy. But it's been pushed or pulled back to this position from its maximum amplitude, either out here or out here. Okay? So here is where it's moving fastest, because that spring has been either pushing or pulling it to that point from its maximum amplitude. Okay? This is where it moves the fastest, so here it's all kinetic. Out here, the spring has been resisting it. Okay, trying to pull it back towards equilibrium until it gets to this point and it stops momentarily. So out here, all the energy is potential. Okay, it's important to remember that stuff. Okay, we've got to know where an object, our mass on the spring, has Kinetic has potential, okay? It's only got potential at these 2 points. It's only got kinetic at this point. Anywhere in between it has both, okay? Just like a roller coaster going up and down hills. All right, questions on that? That's the first half of the unit. Okay, simple harmonic motion, Hooke's law, conservation of energy. That was the first half of the unit. Okay, then we got into waves. All right, so we talked about properties of waves. Okay, there were 2 kinds of waves: transverse, okay, and longitudinal. I don't know how I'm going to draw that. I'm not really happy with that, but okay. Okay, this would be a compression, this would be a rarefaction, this would be a compression, this would be a rarefaction. Remember, a longitudinal wave oscillates in the same plane as it's traveling, whereas a transverse wave oscillates perpendicular to the direction that it's traveling. Okay, so we need to know that. We need to know terminology about waves. We need to know wavelength, period, frequency, okay, amplitude, speed, right, all of that kind of stuff. Okay, all of those are important properties of waves. Okay, we need to remember that a wave is a traveling disturbance. It's not matter, but it needs matter to travel, unless it's a light wave. Okay, but it needs matter or a medium in which to travel. Okay, and that medium can affect the speed at which the wave travels. Okay, all of that stuff is in your notes, but it's all stuff that could be tested in multiple choice questions. Okay, testing your understanding of the properties of wave motion. Okay, so knowing what affects the speed of a wave, knowing what affects the wavelength of a wave, okay, all that kind of stuff, it's all the medium. Okay, we need to understand that. Okay, and we need to know the terminology, not because there's going to be a bunch of questions asking what's the definition of amplitude, okay, but because obviously I will be using that terminology in the questions, and if you don't know what amplitude is, it'll be pretty hard to answer a question that has the word amplitude in it. Okay, so make sure you know what all the terms mean. Okay, then we talked universal wave equation. Okay, so V equals F times lambda, which could also be written lambda over T. Okay, either way will work, right? This is also where we talked about how frequency never changes. Wavelength and speed are dependent on the medium. Okay, so when a wave enters a new medium, its wavelength changes, its speed changes, and that makes sure that its frequency remains the same. Okay, and then we talked about the different kinds of problems that you could get testing the universal wave equation. Okay, so there are some problems that you're going to get that are just about the universal wave equation. But the universal wave equation is also part of other problems that we did, like air columns and standing waves and all of that. Okay, so you're still using the universal wave equation there. Okay, if I'm thinking just of a universal wave equation question, I'm thinking of, you know, a question like there's a person sitting in a boat and they count 5 crests going by, okay, in 10 seconds. What's the speed of the waves, you know, or something like, or the waves are this far apart, you know, what's the speed of the waves? Something along those lines. So you could have a question like that where you'd have to remember that little trick about the number of crests and the number of troughs. Okay, 5 troughs is how many waves? 4. 6 crests is how many waves? 5. It's always one less. Okay, remember, okay, if we're looking at a pattern of waves here, okay, that's 4 crests, but here's where I start. If they're counting crests, they start on this crest. Okay, that's 1 wavelength, 2 wavelengths, 3 wavelengths. Okay, it's full cycles. This is not a full cycle over here. We started here. Okay, that's 1 cycle, 2 cycles, 3 cycles, 4 crests. Okay, everybody all right with that? Okay, so a little thing to remember there. Okay, also remember about echoes. Okay, if there's a question about like sonar or something like that, okay, then we've got sound waves that are traveling to a reflective surface and back again. And you have to remember that for an echo, the time or the distance, okay, is for there and back. Okay, so you have to keep that in mind when you're doing your problem solving. Okay, little tricks, but you know they can trip you up if you're not careful. Okay, so expect you'll probably get a problem like that. Okay, but then obviously we're going to use the universal wave equation for the other stuff that we learned about. Okay, we learned about interference as well. Okay, that's going to be more diagrammatical. Okay, but we do have to remember that interference is governed by the principle of linear superposition. Right, and I told you that the way I'm going to test this is I might do this. So that wave and that wave are occupying the same space at the same time. Draw me a picture of what the resulting shape of the medium would be, or what the resulting waveform would be. Okay, so how do I figure that out? Okay, so first off, are those waves in phase with each other? They are not. Okay, so if you had no idea what I meant by in phase, there's the importance of terminology. Okay, if you don't understand what in phase or out of phase means, you can't do this question, which is fairly mathematically simple. Okay, so they're out of phase. They're completely out of phase with each other because when this one is up, this one is down. What kind of interference is that going to result in? Destructive interference. There's again another terminology thing, right? If you don't remember the two types of interference, you're not going to be able to answer that part of the question. All right, according to linear superposition, if I want to draw what this medium will look like with both of these waves on it, I take their amplitudes and I add them together. Remember, their amplitudes represent their energy. Energy has to be conserved by the medium. So if there's a disturbance that's, let's say, got an amplitude of +3 and another disturbance with an amplitude of -1, the medium is going to show +2. Okay, what's it going to show over here? I got a +1 and a -3. -2. Okay, something like that. That's what it would show. Okay. Definitely going to ask you to do something like that. That's interference and the principle of linear superposition. Okay, I would say that's probably a 3-mark question. Okay, 1 mark for this part, 1 mark for that part, and 1 mark for telling me it's what kind of interference? Destructive interference. Okay, something like that. Pretty easy 3 marks. But again, if you don't remember that terminology, in phase, out of phase, constructive, destructive, you're hooped on a question like that. Okay, and it's really drawing a picture. I mean, it would really suck to be hooped on a picture or a question where all you have to do is draw a picture. Okay, those are easy marks, so we don't want to lose those because we don't know the terms. All right, next thing other thing with interference, okay? That's the 2 speaker questions as well, okay? Interference was 2 speaker questions, right? Where I've got this speaker, I've got an observer here. Do they hear a loud sound or a quiet sound? Okay, so remember, if I know the triangle, so I know how far apart the speakers are, I know how far it is here, I know how far it is from the other speaker to here, okay? I can calculate how many wavelengths there are, okay, from the speaker to the observer, and that will determine, okay, whether they hear a loud sound or a quiet sound. So if on this side there's 2 wavelengths going to that person, and on this side there's only 1, okay, do they hear a loud sound or a quiet sound? Just look at those waves. I drew them in the right way. Are they in phase? Okay. This one's down, this one's down. Okay, I know it's 90 degrees, but okay, they're arriving trough. This person's going to hear loud sound. Okay, and I don't have to draw it to know that. All I would need to do is figure out the wavelength and then know how many wavelengths. So the number of wavelengths here and the number of wavelengths here. Okay, and then I just subtract them. 2 minus 1 equals 1 wavelength difference. If it's a whole number, it's loud. If it's a 0.5, it's quiet. Okay, because if they're arriving 0.5 wavelengths apart, one's a crest and one's a trough. okay? Because a crest and a trough are half a wavelength apart. A trough and a trough are a full wavelength apart, okay? So they arrive in phase, constructive interference, it's loud, okay? They arrive half a wavelength out, if they're out of phase, it's destructive interference, it's quiet. Right, so we got to remember how to do those. You've got a number of examples in your notes about how to do those. Okay, so make sure you've looked those over. Okay, waves at a boundary. Okay, so this is going to be again probably like picture type of questions in the multiple choice. All right, so if I've got so this is my before picture. I've got that going that way. Okay. My after picture may look like this. Sorry, that needs to be. I didn't really give myself enough room here. And that's not what I want to draw. Okay. Okay, so blue is before, green is after. Is the second medium more or less dense than the first? How do we always tell? There's two ways to tell. One of them has to do with the reflected wave, and the other has to do with the transmitted wave.
If the pulse is upright, inverted.
Right. Okay, so my reflected pulse is upright. Okay, it's a crest. The incident wave was also a crest. So I have an upright reflection going back. Okay, and I have a transmitted wave that's longer than my incident wave. Okay, so is that second medium more or less dense? Okay, let me say it a different way. Is the second medium faster or slower? The wavelength got bigger. What happened to the speed?
Got slower. Faster.
Got faster. Remember, wavelength goes up, speed has to go up, otherwise frequency will change. Okay? They have to do the same thing according to the universal wave equation. Right? So in this situation, I am going from a more dense medium to a less dense medium because my wave sped up, got longer, and my reflection was upright. Okay? That, I think you guys had better go over. Right? You have to have that stuff kind of memorized. Right, in order to do these kinds of questions. I got to be able to look at this and go, okay, I really only need to know one or the other. Okay, upright reflection, going into a faster medium. Okay, longer wave, going into a faster medium. It's one or the other. Okay, you don't need to necessarily know them both. Okay, because they both happen together. Right, if that was an inverted reflection, then the second medium would have been more dense. Okay, you only get a reflected wave that's inverted if it's going to a more dense medium. All right, so that's something you have to have memorized as well. All right, then we talked about standing waves after that. So this will be your air column question. I told you there'd be an air column question on your test. I'm not going to tell you whether it's open or closed, okay, because I want you to study both. But remember that with air columns, okay, with a closed air column, lambda equals 4 times the length of the tube because at the fundamental frequency, there is 1/4 of a wavelength in the tube. Other thing to remember, with closed air columns, we only get antinodes at the top at F1, at F3, 5. Okay, you got to remember that. Okay, in case a question tries to be tricky and says calculate F1 and then ask something like, what's the next frequency you would hear? Well, not F2. Why not? It's destructive, right? There's no sound to hear at F2. Doesn't mean there's not a wave there, but there's nothing to hear at that frequency. You only hear stuff at odd numbered frequencies for your closed air columns, right? This is what F2 looks like. It's a node at the top, okay? F3 looks like that. Okay, 3/4 of a wave. Antinode at the top, we hear a sound, right? With our closed air columns, or sorry, with our open air columns, okay, so open at both ends, lambda equals 2L for the fundamental frequency because there's half a wavelength in the tube, okay, at that first resonant point. Okay? How are open air columns different in terms of the sounds they make? They resonate at every frequency. Okay? There's always, because there's always a difference of a half a wavelength instead of a quarter of a wavelength, every half a wavelength is another antinode. Right? So you always get a sound because every half a wavelength is a new pattern and every half a wavelength is a new antinode. There's never nodes at both ends of an open air column. Okay? So F2 would have a full wavelength in the tube with antinodes at both ends, and so on and so on. Okay? So important to go over that. Okay? That's something you'll need to know. Okay, and then, sorry, standing waves was air columns, but standing waves also, remember your terminology. So if we're looking at, let's say, like a spring, okay, like what we did in class, or rather what I did and you watched, okay, okay, standing wave patterns, there's nodes and antinodes, okay, things like that. Just understand how standing waves are the result of patterns of interference. They're the result of reflected waves interfering with produced waves, okay, and they're all the same wavelength, they're in the same mediums, they travel at the same speed, okay, that kind of stuff. There could be some multiple choice about that. Okay, so we already did air columns, and then Doppler effect's the last thing, right? There's going to be a couple of questions in the multiple choice about Doppler effect. Okay, understanding whether you hear a higher frequency or a lower frequency is likely what they're going to test, okay, given the situation. What the hell is going on? Okay, and expect a Doppler effect problem in the written response. Okay. Obviously, moving source. That's all we do. Okay. Questions on that? Anything you guys want me to review in more detail?
Could you do a two-speaker question?
Yes, but you have to give me about 10 minutes
Okay.
because I have to figure it out. It's actually, to build one of those, I actually have to get all the numbers right. I can't just make up numbers or it won't work. So give me about 10 minutes and I'll make one up and do it on the board here. Okay? So give me 10 minutes and I'll do a two-speaker question for us to try. Okay? but I'll type it so you can read it. Okay, give that one a try, and then I'll walk you through it.
go over that one, or do you still need a few minutes?
Good. Oh, I was probably recording this the whole time. Yep. Big dead spot in the middle of that. Okay, so two speakers are 2.815 meters apart. So we've got this situation here. They are 2.815 meters apart, and the observer is 1.625 meters in front of one of them. Okay. This is the other side of the triangle here. Okay. We know that the speed of sound is 340 meters per second, and we know that the frequency of the sound is 523 hertz. All right, so we need to find the wavelength of the sound. Okay, to find the wavelength of the sound, then we can find the number of wavelengths from each speaker to the person. All right, so first thing to do is find the wavelength. Sorry, wavelength will equal V over F. Okay, just manipulating the universal wave equation. So 340 over 523. All right, so 0.65 meters. All right, so now that I've got that, now I need to calculate how many wavelengths there are from each speaker. First thing I need to do then is figure out how far it is from the second speaker to the observer using Pythagorean theorem. Okay, so we'll have square root of 2.815 squared plus 1.625 squared. Right, gives us 3.25 meters. All right, so now that I know that, now I can calculate the number of wavelengths in each side. Okay, and I simply do that by taking the distance and dividing it by the wavelength, which I found to be 0.65. All right, I'll keep all my decimals here just so that I'm following all the rules of motion here. So 1.625 divided by okay, so that's 2.5. Okay, so there's 2.5 wavelengths here. All right, and then I got to do the same thing here. So I'm going to take the 3.25 and divide by 0.65. Actually, I'll, again, use all my decimals here. So oops. Oh, crap. Gotta try that again. And that number divided by that one. All right, and that's 5. Okay, so all right, so I got 2.5 wavelengths from one speaker, 5 wavelengths from the other. And we always said that whether they hear a loud or quiet sound depends on the difference between them. Well, the difference between them is 2.5 wavelengths. So, okay, so this is 1 wavelength, that's 2 wavelengths and a half, and this is 5 wavelengths. So we've got 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, whoops, 5 wavelengths. Are they arriving in phase? No, they're half a wavelength out of phase, which means they're totally out of phase, and we are looking at complete destructive interference, and thus a quiet sound. Okay. All right? Okay. And they all work basically the same way. Okay? It's always the same set of steps to get those. Right? I almost toyed with telling you that it was a loud sound, that they heard a loud sound, and making you work backwards to find the wavelength, and I thought better of it. Okay, what else?
Could you please do another Doppler effect?
Another Doppler effect question, sure. Okay. Okay, give you a couple minutes on that one. All right, so for this one, okay, first thing we have to do is calculate the speed of sound, because they give us a temperature there. So 332 plus 0.6 times 32 degrees. And so 332 plus 0.6 times 32, right, 351.2 meters per second. All right, so now we got V, okay, we are told Vs, the speed of the source, is 180 meters per second. We're told it's approaching, so we know we're going to subtract on the bottom, and we know that the perceived sound, okay, what the observer hears, or F, is 925 hertz. Okay, so there's the information we're given. The Doppler effect formula says the perceived frequency equals the actual frequency multiplied by V over V, in this case, minus Vs, because we have an approaching source. All right, so we're manipulating for FO. Right? I'm just going to leave FO where it is and bring the brackets over to the other side by dividing them. All right, so F divided by V over V minus Vs will give me FO. Everybody okay with that manipulation? Right, so now all I have to do is plug in my numbers. 925 hertz divided by 351.2 over 351.2 minus 180. Okay. Are these frequencies going to be quite different? Yeah, the faster you go, the more the Doppler effect is pronounced. Okay, so when we plug in our numbers here, we'll have 925 okay, divided by, in brackets, 351.2 divided by 351.2 minus 180. All right, so the actual frequency of the jet is 451. Actually, I think we only have two significant digits, so 4.5 times 10 to the 2 hertz. Is the actual frequency of the plane. Okay. All right. Hey, what else, guys?
Like a bombing boat question.
Bombing boat question. Okay. I almost wrote on a bat. Okay, person is on a boat. Okay, that is bobbing up and down. Seconds. Okay. 30 meters away from another boat. Well, this is gonna be a good one. Okay. Trough. Doesn't it look right either way? It's GH. Yeah, didn't look right. In a true trough. Okay. How fast are the waves moving? You'll have to draw it. Only way you'll be able to do it. Unless you're just incredibly good at picturing things in your head. How fast are the waves moving? Okay, that's a tricky one. Oh, that was such a great question. Okay, there's the answer. Sorry. Okay. What else do we want to go over?
Just like a simple harmonic.
Okay, so like what kind of like calculating the period of a pendulum or mass on a spring? Give me a minute to try that one. All right, so what we're given in this one is the length of the pendulum, okay, 1.2 meters. We're also told the period of the pendulum, 2.5 seconds. Period of a pendulum is 2 pi times the square root of L over G. We're looking for G. If I want to find something under the root, what do I have to do to everything? Square it. Okay, so T squared equals 4 pi squared times L over G. And then if I want to find G, I'm just going to swap it with T squared. Okay, so I'm going to have G equals 4 pi squared times L over T squared. So that'll be 4 pi squared times 1.2 meters divided by 2.5 squared. Okay, most common mistake there is forgetting to square the 2.5. Okay, so we've got 4 pi squared times 1.2 divided by 2.5 squared. Okay, so acceleration due to gravity there is 7.6 meters per second squared. Okay. What else? Conservation of energy one? Okay. Okay, give that one a try. Okay, so here's what we know. Okay, we know what K is. It's 2.5 newtons per meter. All right, we know it's oscillating with simple harmonic motion. Saying it's oscillating with simple harmonic motion and mentioning how fast it's moving eliminates Hooke's law from this. Okay, we know this isn't a Hooke's law question for two reasons. I was asked to do a law of conservation of energy question, and secondly because this one talks about speed in 2 different points. Okay, so we're looking for V final, we'll say. Okay, we don't know what it is. We do know the maximum amplitude is 0.65 meters, and we know that XF, okay, our other displacement, is 0.22 meters, and we know the mass is 1.5 kilograms. All right, given that information, talking about two different points, the only way I can calculate the speed is by setting the mechanical energy of the 2 points I'm given equal to each other. Okay? So my first point is going to be my maximum amplitude, where I only have what kind of energy? I only have potential energy. All right, so I'm just going to go 1/2 Ka squared. Okay, that's my initial energy. Okay, at the second point, I'm not at equilibrium, and I'm not at the maximum amplitude, so I have both kinds of energy. So I'm going to have 1/2 Kxf squared plus 1/2 mvf squared. All right, so that's what I've got there. I'm trying to find Vf. First thing I'm going to do, cancel off the halves. It's in every term, so I don't need it. Okay, then I'm going to subtract Kxf over to the other side. So I'm going to have Ka squared minus Kxf squared equals mvf squared. Divide both sides by m and square root, and I've got Vf. Right? So when I plug in my numbers here, okay, I'm going to have 2.5, that was K, times 0.65 squared. Most common mistake here will be forgetting to square the x's. Right? Minus 2.5 times 0.22 squared divided by 1.5. Right? So that'll get me my Vf. Okay, so square root of 2.5 times 0.65 squared, minus, oh, I should have hit that in brackets. Oh, too far. Actually, I should have had it in 2 sets of brackets. Okay, so minus 2.5 times 0.22 squared in the brackets divided by 1.5 in the brackets. All right, so the speed there will be 0.79 meters per second. That would be about as tricky as they would get. Yeah. All righty. Anything else? All right, well, you've still got a few minutes here. Okay, you can look at the review package there. Okay, like I said, it's extensive. You probably don't need to do all of it, but I don't know why it ended up being so extensive. It just did. Okay, so you can have a look at that, and then as soon as I get back, I'm just going to step up for one quick sec. I will start spraying down desks. Okay, so at that point, we'll need to be all masked up and ready to wipe stuff down. Okay. Okay, let's get everybody masked up and I'll come around with the soapy water.
It's still got your work.
Okay, so tomorrow, guys, we will start final exam review. Okay, and then you'll write your test on Thursday. Are they out, or do they have to go in to get out?
No, just looking today.
Well, I'll say a prayer for you.
I've been able to get it like online.
Yeah, it's so weird, right? Like they either impact one another too, that they come out sideways. Wisdom to
I will. If anyone disturbs me, I'm just so
Yeah, not everybody gets them. I have them, they're all stupid. None of them ever came out.
Yeah. I love it when they hit you with the own It really makes you feel great about yourself.
Yeah.
The saddest part of mine is to make
Look
you
at
more
those
proud.
teeth. There's an extra set of molars, top and bottom. Our children would really be able to chew their.
Oh no, that's a consideration of the past. If I ever get pregnant, then I have to consider, I have to consider the importance of teeth. I have to use this twice.
All right, guys, we'll see you tomorrow. Okay. So all there is to Hooke's law would be you have something hanging from the ceiling. Okay, the mass like this, and you'd be asked to calculate something like. Okay, and then you would just go fx equals mg, so you have negative k times x equals mg, and you're solving for x. Yeah? Well, the horizontal one, it would be that this is the only force. It would be, so it would be fs equals m times a, and it would be the net force. So it would ask you, give you the same information, but ask you to calculate like acceleration, or give you the acceleration and ask you to calculate x or k. Yep. You too. Hey guys.
summer, she said it tugs on a lot of hair. So I was like, no, I'm good. So I'm excited to see the people who forgot. It was great. Yeah, that's the only reason I did, just to avoid the pain.
Yeah.
In any other circumstance, not a chance, but I just didn't. See, it's this thing. Awesome.
It's this thing.
You did on our wrist yesterday?
I don't think you're supposed to.
No, you did.
No, it's fine.
How's it going, guys? Anybody have any questions or anything they want answered or go over?